Any other questions about aromaticity or yes?
I have a question about the lab, but I left my lab manual at home. I seen something about, it said wash with water, we're supposed to put a solution in water once we get done.
To triturate it?
Yeah.
Triturating
Do we do that inside a separating foam, or do we just pour it in the water? I was confused.
No, it's not going to be a solution, it's a solid.
Yeah.
You know, put solids in separatory foam. Just wash it.
Oh, okay. I gotcha. All right.
Wash it in a solid. Yes. Uh-huh. Any other questions, guys? Yes?
Do you collect your exams back up, or do you keep them?
No, you keep them.
Okay.
You need to be able to review, right? Learn from your mistakes. Ask questions. Yes. Do you not get to keep your other tests?
Usually no.
In which class?
Most of my science ones.
You don't get to keep any of your tests?
A lot of teachers like to reuse the same test so they don't give it out so that other students can look at the answer.
Okay. Well, I mean, there's plenty of my tests out there, but that's not going to. That's only going to hurt you by doing that. No, I prefer you have it so you have a history of what you've done and you can learn and review. Yeah. Okay. Any questions about aromaticity? Okay, I think we finished it up unless otherwise. Time to move on to reactions of aromatics. We have a tan colored one and a white one. The white one says EAS at the top. Some warm-up questions there. Back to the first page. Mechanisms for aromatics. There's 3 general reaction mechanisms. 1, 2, and 3. Okay? EAS is the most common, most diverse. We'll see the most examples of EAS. Okay? The other ring reacts with an electrophile. We'll also have an NAS version where the ring reacts with a nucleophile. And then we'll have a benzyne mechanism. Okay? These are all essentially substitution mechanisms. You can read the information here. The first is EAS. And we can do lots of substitutions by EAS. And this shows some examples. Or I think all of our examples we'll be looking at. Okay, start with benzene. Now we will have substituents on benzene eventually, but here just benzene, and I'm showing an H because that H is going to be replaced in the substitution mechanism. Okay, electrophilic aromatic substitution, EAS. And we can replace the H essentially with halogen. We can halogenate the ring. We can sulfonate the ring. We can nitrate the ring, which we're doing this week in lab, nitration of an aromatic. All right. We can also put carbon groups on the ring. That's the blue handout, 3O crafts. Okay, we'll get to that. We can also put a acyl group. Carbonyl R group, often called an acyl group. Ketone group, but it's acyl. Now we'll do additional things. For example, the acyl group can be removed, or the oxygen can be removed, and it becomes CH2R, but CH2R can just be called R. The nitro group, once it's put on the ring, we can reduce it to the amino group, and you'll be doing that in the lab next week. Okay. And then from the amine, we can actually replace the amine with various groups, and that's called diazonium chemistry. We'll see that. So in addition to EAS, I'm also showing a couple of other miscellaneous reactions on this scheme. But basically, this is the overview. We'll be looking at each of these reactions. And the first, I believe, we'll be looking at halogenation. And this is our outline, and we'll need to look at the mechanism, including rate determining step. And we'll be heading down this. But most of this is shown on the white page, white handout. So the EAS mechanism. The ring is reacting with an electrophile, some type of electron poor species. It may be positively charged, but a lot of times it will not be. But it will be electron poor. Okay? Same old thing for electrophiles. Very general depiction of EAS. Mechanism. Now the benzene ring is aromatic. We know that it's really not three alkenes. Okay? It's really one continuous pi system and all that aromaticity discussion there. But when we do a mechanism, we can treat it as if it's just sort of like an alkene. Okay? We're going to use one alkene, just like an alkene chemistry in organic 1. Okay? Now, it's much less reactive than a standard alkene. In organic 1, when we were doing alkene reactions, if we had a benzene ring in the molecule, I said, don't do any chemistry with the benzene. Not in this class. Because typically, to get the benzene to react, it has to be more reactive reagents. Okay? But the reagents we're going to be using are more reactive. And so the benzene will react even though it's aromatic. And in organic 1, when we did alkene reactions, the first question is where we're going to leave cation. Top or bottom, right or left? Remember that question? Those questions? Where are you going to leave cation? Well, where would you leave cation? Top or bottom? Doesn't matter. It's symmetrical alkene right there. Okay. So I kind of swung it out and I left cation at the bottom, right? This carbon bonds to electrophile. Still an H there, right? There is an H there. We make this carbocation. This is called your sigma complex because we just made a sigma bond to the electrophile. And the sigma complex is not aromatic any longer because this carbon is no longer has a p orbital. That carbon is now sp3, no p orbital. So it's no longer aromatic. It's also charged. So this is much higher energy than this. Anybody agree? Okay. Now, even though it's not aromatic, it is resonance stabilized. Okay, we can windshield wiper this over. And resonance for the sigma complex is shown below. It should be nothing new. Could you draw resonance structures of the carbocation? Yes. Windshield wiper over, that's the terminology I use, windshield wiper. Yeah. Get this resonance structure, then we can pull this down, show this resonance structure, and that's it. But there's 3 resonance structures here. We can draw the hybrid, understand the hybrid. Charge is delocalized. Now, what's the fate of the carbocation? Typically, carbocations, nucleophiles can add. If something added here, this can be a base or a nucleophile. But if whatever that is added here, you'd have a bond of that to that. But that's not the product. That would be an addition reaction, where we add E and B. This is not the product because it's no longer aromatic. You now have 2 sp3 carbons. Instead of doing addition by some nucleophile adding to the carbocation, we typically always eliminate. And instead, something is going to act as a base and take this H that was there originally. Then the electrons can move back in. And what does that give? That restores the aromaticity. And that's the more favored outcome. Okay? And this looks like the second step of an E1 elimination, where we make carbocation and then something takes the H to put the double bond in. Okay. So we can compare two reaction coordinate diagrams down here. Shown above, reacting with the electrophile to make a sigma complex. It's higher energy because it's charged. It's no longer aromatic, but it is resonance stabilized. And being able to show and understand the resonance will be important more and more as we move forward. From there, we can either do what ultimately is going to be called an addition reaction. But this product would be higher energy than this product because it's not aromatic, but this is. So which is going to be favored? Forming this. Why?
Lower energy.
Not so much because it's more stable, but why?
It's aromatic. It's lower energy.
No, why is this formed?
Conjugate?
Hmm?
Conjugate?
It's more stable because it's conjugated, but why is it formed? Not because it's more stable, but because what? Hmm? No, we've already said all that. It's very stable because it's aromatic. Why is it formed though? You're just missing my question. It's formed because the activation energy leading to it is lower. Okay? It's a fine detail. It ain't formed because it's more stable. You can say that's it, but that ain't really why it's formed. The reason it's formed is because the activation energy leading to it is lower. Right? I can give you scenarios where the more stable, where the lowest activation energy led to the less stable product. Then your answer would be wrong. I want you to give an answer that applies 100% of the time. And the answer that applies 100% of the time is this is formed not because it's stable. That's secondary. The reason it's formed is because right here, the activation energy leading to it is lower. That's the answer. Now, usually, a more stable product is going to have a lower activation energy. But that's not always the case. We talked about that when we did 1,2 versus 1,4 additions in organic 1. Yeah? Because when you do a 1,4 addition, which is the more stable product, the activation energy is actually higher. Okay, now if this was just a regular alkene, maybe just one, how would you react with something like bromine? You would do an addition reaction, okay? Benzene doesn't do addition reactions. Instead, it does this substitution, and H gets replaced because an H gets removed from the sigma complex. So ultimately, the H is getting replaced by the electrophile. Substitution. Okay? All right, first type of EAS, specific type, is going to be halogenation. The most common is chlorination or bromination. Bromine. Now, an alkene reacts with bromine instantaneous. You did it in lab with me, right? Hand behind your back. Benzene does not react instantaneously with bromine. Okay? It's aromatic, the electrons are busy being delocalized, it's less reactive. But you can get it to react. Now usually you have to include a catalyst, a Lewis acid catalyst, such as FeBr3. Which color? The FeBr3 here is a Lewis acid. Definition of Lewis acid? Except accepts a lone pair? Yes. The mechanism here is your bromine these electrons first add to the iron, and that gives I'll draw it out. Lots of bromines here, yeah? I'll just put lone pairs here. What's the charge of this bromine now? Positive. What's the charge of the iron?
Minus.
How do you know it's minus?
Because it would normally be iron 3 with your 3 bromines and it's neutral, so then you've added more electrons, so then it's minus.
Good. You see that if you do that, it owns 1, 2, 3. Apparently it's neutral. I showed it as neutral. But here it's only 4. That's one more. So if it's neutral here and it's only one more, it must be minus. Yes, it is minus. And also everything over here is neutral, so everything over here has to be net neutral. So if you created a plus, you've got to have a minus somewhere. Yes. Okay. And you see how the iron accepted a lone pair? The Lewis acid. See, transition metals have d orbitals, and often empty d orbitals. And transition metals are thus often Lewis acids. Okay? Now, how do you make oxygen a better leaving group? Protonated, which makes the oxygen positive. Okay? Ultimately, we made this bromine positive, and it's going to be a better leaving group. All right? At this point, I won't redraw the ring. We do our EAS mechanism. But this is our electrophile. Okay? But the thing that we attack is this bromine. And so these electrons attack this bromine, and we kick these off, like a leaving group. And now we're just doing the EAS mechanism on the front page. And so what does this give? All right. Now on the front page, I think I might have went up. Here I pulled these down. They bond to bromine. Plus here. Plus what? Plus that? Uh-huh. Here's your resonance stabilized sigma complex. What's the next step? What's the next step?
One of bromine will take the nitrogen.
Okay.
The bromine will take the nitrogen, but off of
Okay. We have a hydrogen here. Many of you will not know where H's are. Please make sure you know where H's are. There's an H there. That's the one we're removing. Okay? Now, my molecule is going to be turned a little bit. I see my bromine is up, not down. Okay. But this carbon no longer has an H, right? Every carbon here has an H. The one there has to be removed. Something takes it. This is probably the first time I've ever done this. Iron is no longer happy. Iron doesn't want to be minus. Why did it do this? Well, we made it do it. Now the bromine sort of breaks away from the iron, and these electrons that are bonded, these electrons break away from the iron, come over here and bond to the H. These two electrons move in here to put the pi bond in. And what does all this give? When we put the double bond in, it gives bromobenzene. Plus what? What else was formed here? HBr plus what? Now we're left with FeBr3 reformed, and so what is that? Catalyst, right? The reformed rare catalyst. It's there at the end. And so you do produce HBr, and okay, so this is a specific example of our EAS mechanism. Yes.
So, when you look at the mechanism, you see how the bromine would attack the H. Do you show the bromine kind of like being eliminated from the iron first?
You mean just leaving on its own?
Yeah.
You possibly could show it that way. It's probably a little bit vague. That is this in equilibrium with maybe FeBr3 plus Br minus? That's what you're saying, right? Maybe the bromine just leaves, and then it takes the H, and you get the same outcome? Possible, I don't know if this is known. Typically it's shown like I showed it. You know. This, you know, it's very well. But guess, ultimately we're very formal with this because it depends on the solvent. HBr may be ionized anyway. And if HBr is ionized, then it ain't HBr, it's really this and H+. And so there's a lot of minor variations that could be from this. Okay? All right. We illustrate how the FeBr3 is a Lewis acid. And basically, if you don't have this, or the other way around, this does what? It makes bromine more electrophilic because we made one of the bromines positive. And now it's really going to want to break away. And this being positive actually creates a dipole here. And so that's why this N-bromine actually has some partial positives. And the N-bromine is the electrophile. So just because we show electrophiles with a positive charge doesn't mean that that one's going to be the electrophile. This just means that an electron-poor species. And this bromine's electron-poor because that bromine is mad and saying, hey, I got to have some electrons, and so it steals them from this one, and there's actually some partial positives here. And so in many of your mechanisms, you have to think about these fine details that are just sort of there. Question?
So the Lewis acid says FeX or ALX3 on both, three on both. Does it have to be the same halogen as?
Typically, you keep it the same halogen. Yeah, it's just commonly. It may not actually have to be, because I don't think you're going to scramble your halogen. Typically, it is. Okay, either FeX3 or aluminum. These are your most common Lewis acids for aromatic reactions. Like aluminum, AlBr3. Or more common, AlCl3 is very common, aluminum trichloride. Okay? You can also actually use the metal. Sometimes you'll see like bromine and just iron metal, Fe. That's because iron metal and bromine actually react to form what? Your catalyst. And so this is called a pre-catalyst, and it reacts in the reaction to give your actual catalyst in situ. Okay? Now, why would you want to do that? Well, because these things here are actually pretty sensitive to like moisture in the air. They can be hard to store. Okay? You buy them and a year or two later they are like you've soaked up water and they're no longer good. Where iron, you can buy it and in 100 years it'll be good. Well, it could rust, but it ain't going to rust as fast as these would do something. And so it's more stable, and so people kind of sometimes prefer to just have that around. Just put that in. But it's going to just react with some of the bromine. Just use one more molecule of bromine than you would. Okay. Form your catalyst in situ. And so you can do this with bromine or chlorine. With iodine, you typically need to include an oxidant to actually form I+. And Lewis acid complexation doesn't work with iodine. Typically need to form I+. I+ can be formed by treating elemental iodine with some type of oxidant. We actually did this 2 weeks ago in lab when you used iodine paper. The oxidant was calcium hypochlorite. Okay? No, we were doing a different oxidation. We were going from I- to I2. So this gets oxidized to I2. But I2, which is an oxidation state of 0, can actually be oxidized again to I+. Common oxidants for this are copper 2 chloride, hydrogen peroxide, hydrogen periodate, even nitric acid can do this. Problem is with nitric acid, sometimes you get nitration instead of iodination. So you're going to be careful with using nitric acid as an oxidant. So, I show an example reaction here. Here the copper is actually an oxidant. I'm not going to show full mechanism. Basically the mechanism is you're going to form I+ here. And then the mechanism is on the front page. You just replace E+ with I+. Okay? Now when we did bromination, did we form just a single Br+? No. There was a Br+ on the board, but it was complex with iron and another bromine. And it really wasn't oxidized. Down here we're actually forming I+, and that is an oxidation. F2. Typically, we don't do much chemistry at all with F2. It's too reactive, and thus reactions are too exothermic. And they have a tendency to explode sometimes. And so you're rarely going to see use of F2. Very exothermic because the CF bond is very strong while the FF bond is very weak. And so making carbon-fluorine bonds, typically very exothermic. Now there are some specialized reagents you can use for fluorination. One of them is this pyridinium NF compound. And a nucleophile can attack the F and this positive nitrogen can leave. I've got some of these type of reagents. There's nice stable solids, okay, where F2 is a very toxic gas. It'll chase you around the room if you let it get away. Nice solid, much easier to handle, okay. The better way to get a fluorine on the ring is going to be diazonium chemistry. We'll see that a little bit later. Okay, much better way to get a fluorine on the ring. Okay, nitration of aromatics. Treat an aromatic with nitric acid and very often an H+ catalyst, we can get nitration. And name of this compound? Nitrobenzene. I think there's 7 aromatics to know. Question?
Do you know a mechanism for the I2 oxidation?
The actual oxidation?
No.
No. It's probably redox, radical. Oxidation, redox mechanisms are often very hard to beat. They're often not clear. Okay, we can make nitrobenzene. Low structure of the nitro group coming off the ring. Okay, we're going to have two charges here. When we condense it to NO2, really you get no full structure. Okay, there's no way to draw it where everything's neutral. It's going to always have two charges. It's basically analogous to what is that group? That is, instead of nitrogen, carbon.
Carboxyl.
I can't hear you.
Is it a carboxyl?
Carboxyl. It's okay. I prefer, I think, more appropriate, carboxylate. Carboxylate anion. Yeah. I mean, really the only difference is change this to nitrogen. Right? But since it's now nitrogen, nitrogen having 4 bonds like that is what? Positive. But now, since it's a positive negative, it's net neutral and you don't need anything else there. Where if it was a carboxylate, you need to have a plus to balance the minus, and you'd have maybe a sodium carboxylate or something. Okay. All right. The electrophile here is the NO2 ion, nitronium ion, and Lewis structure of that is here, and the nitrogen is actually positive. And so, how do we form the nitronium ion? It comes from nitric acid, and nitric acid is going to be HNO3. This here is nitric acid. Is that right? Okay. What do we have to lose to get the nitronium ion? We need to lose an oxygen, this OH, and this can become, oh, yeah. So this oxygen has to leave. How do you make oxygen a better leaving group? Protonated. What's the H plus catalyst for? Yes. We protonate nitric acid. Can you imagine that? Nitric acid is a strong acid. We're protonating a strong acid. Think about it. That's very weird. Yeah? But protonated, what does that give? That there? Now, how can we get the nitronium ion? These electrons do what? Come in here. Kick that off. I've said this before. We'll say it many times going forward again and again and again. Anytime you can make a pi bond kick off a leaving group, easy to do. That's what we did here. What does this electron movement give? Gives that, plus what? Yeah. What acid would you use here? What acid could protonate nitric acid? Most common is sulfuric acid. That's the most common. It's actually a little stronger than nitric acid. One strong acid protonating another. But actually nitric acid can protonate itself.
Does it just pull an H from another nitric acid?
Yeah,
and then
there's a gazillion molecules.
Right, so it'll steal them.
Right. Nitric acid can protonate itself. So you don't always have to use sulfuric acid.
Is that why we don't have to use acid today?
Yeah, that's one reason. The other reason is if you do use sulfuric acid, the reaction is going to be more reactive. Well, sulfuric acid is going to be a more catalytic effect than nitrogen. And with fluorine, you don't want it to be more reactive because fluorine is already more reactive than benzene. If we tried to use sulfuric acid in the reaction we're doing this week, you're more likely to get dinitro.
Okay.
Because the reaction with sulfuric acid is easier, and you can start doing multiple nitrations. And so it's just not needed. In that case, the catalyst would be causing problems, side reactions. But traditionally, sulfuric acid is used. Okay. Once we get the nitronium ion, well, then the benzene ring, these electrons, how about if I swing them up? They come up and attack the nitrogen, and one of these gets moved over. Your choice. What would that give? This is bonded to nitrogen. One double bond remaining to oxygen. The other becomes what? Right here. Everything is in your arrow movement. Okay, guys? Some of you, I don't think quite get that in the mechanism on your test. The nitrogen is still positive.
Go ahead. I'm still waiting.
The door is banging. We're trying to figure out if somebody's trying to get in, but it's the wind.
I stopped that one. I didn't know this one did it. Is it because it's windy today?
Yeah.
And there's your nitro group. And there's an H here, right? There's pi bond here and here, and positive here. There's your sigma complex. And what's the next step? We got to restore the aromaticity. What can take the H? Is there a minus up here anywhere? Yes. There's one right here, HSO4 minus, if we use, okay? And if we use HSO4 minus, and another thing, guys, in a mechanism, you never use a condensed structure in a mechanism. Okay? Also this, H plus, okay? Just throwing something at a like that is no good. Okay? And having a condensed structure and then showing some arrow like that, no good. You need to show your bonds in and never use condensed structures. Unless maybe water or HBr or something very small, okay? But something like this is no good. For example, the reason it's no good is there's no HN bond in nitric acid. So if you have a full structure, this looks like you're trying to break an HN bond. I don't know what this is, but I see this a good bit. I mean, I saw this a good bit on the test. Okay? These electrons, anytime you do an arrow movement, what do we say? These electrons take the H, these move in. What does this give? That gives that, and we reform what? We reform our catalyst. All right?
If we don't have the sulfuric acid, is it just water that comes in and steals that H then?
Or you use nitric acid as the acid.
Okay,
And so
that's right,
you
'cause
would
it's
have
lost.
one nitric acid to react, and the other would be the catalyst.
Right, okay,
And you would come in with, this would be nitrate coming to take an H.
okay.
Okay, nitro groups are commonly reduced to amino groups. And this is a common way to make an aniline, aminobenzene. Okay? Because it's very difficult to put an NH2 directly on the ring. We typically always first nitrate, then reduce. A two-step process to anilines. The nitro group is reduced a couple of different ways. One is usually an active metal. And examples are iron, tin, or zinc. And this is called a dissolving metal reduction, because metals are not soluble. But after this reaction, they're going to become ions and soluble. So the metal dissolves. It's just a simple term, dissolving metal reduction. This does require H+. We're not going to look at mechanism here. It's redox. The nitrogen's getting reduced. Reduced. How do we know that? We're adding H's to it. That's a reduction. It's also losing oxygen. That looks like a reduction. The nitrogen's getting reduced. That means something gets oxidized. What gets oxidized? The metals. So the metals become metal ions, like Fe2+, or zinc 2+. And once they become ions, they become dissolved. Because usually this has a good bit of water in there. Now, I'm not going to show mechanism. It's probably radical redox. But I will point out this. These metals, as you learned in Gen Chem, hopefully, will react with acid to become oxidized and generate H2 gas. Okay? Now, another way to reduce the nitro group is actually to use H2 gas. A hydrogenation, using a traditional hydrogenation catalyst such as palladium, platinum, or nickel. And this will also reduce the nitro group to the amino. Now in lab next week, how are you reducing your nitrofluorine? There were two methods, but one I said we're not going to use. Two metals.
Zinc? Zinc?
Zinc. And what was the other one shown? Tin. Yes, zinc or tin were the two options, but I told you nobody should do the tin. Hard to filter. All right. So you'll be using zinc. Zinc and some type of H+ source to reduce your next, sulfonation of aromatics. If you react benzene or an aromatic with SO3 with sulfuric acid catalyst, we can get a sulfonic acid structure here. And this is called benzene sulfonic acid. What's the electrophile here? Look at SO3. You can do different Lewis structures here. In this structure, the sulfur has an expanded octet, 2, 4, 6, 8, 10, 12. That is possible for sulfur. Okay. Now with the acid catalyst, one of these oxygens becomes protonated. And I'm skipping that on the board. Can everybody do protonation of that oxygen? Okay. You can't skip such steps on quizzes or tests. All right? So you protonate your SO3. Now that increases the pooling here, and it makes the sulfur more electrophilic. Now the benzene, I'll pull these down, the benzene attacks the sulfur, and these electrons get moved to oxygen, which wanted the electrons anyway. And what does that electron movement give? I pull those down, bond to sulfur. We have double bond to oxygen, another double bond to oxygen. And the other one now is what? single bond OH. That's a plus. I'm not drawing any resonance structures here. You should be able to draw resonance. Resonance stabilized sigma complex, H here. Now that right there is your sulfonic acid. What do we need to do? Restore the aromaticity. What can take the H? Yeah, there's a these electrons take the H, these electrons move in, make the pi bond. There you go. And we reform H2SO4. Now last comment here, this reaction is actually readily reversible. Readily reversible. We can come back here. That is this. What does this have to attack to get back to here? H plus. Can an alkene attack H plus? As the first alkene reaction we did in organic 1 was attacking H plus. Here the aromatic alkene pi bond attacks H plus. And from there, this can come backwards, and it would lose what? It can lose SO3 and go back to benzene. Okay? You should look at the reverse mechanism. All right? And the mechanism, all the mechanism is moving electrons to get to where you need to go. Can everybody move electrons? So, please do the reverse mechanism of that. Benzene sulfonic acid going back to benzene. I see some of you in lab this afternoon upstairs. We'll get started at exactly 2:30. Have a good day, guys.
Why is but like in the product, like like typically just single bonds.
When we just show NO2, we're not showing charges. It shows this.
Okay.
Just like if I showed you this. You see two charges there, right?
Yeah.
Okay. The NO2 has two charges, but it's not neutral. I mean, we just showed NO2. Yes, if you want to show full structure, then that's full structure.